All right, here's an overview of LT5A solving word problems from our motion unit. We're first going to look at scenarios when an object is traveling at a constant speed. On a position versus time graph, a constant speed is a straight line. Well, to write the equation of that line, we would write y equals mx plus b, just like you've done in math class. But in physics class, each of these variables has a specific physical meaning. So in math class, we'd write y, but in physics class for this graph, we'd write position. So what we're going to do is we're going to take this equation here and we're going to write it again over here. So instead of y, let's see here, we write position. Instead of m for slope, we're going to write velocity because we learned that the steepness of the position versus time graph tells us the velocity. Instead of our x variable, we're going to write time. And instead of y-intercept, we write initial position because those are just the meaning of each of those things on our position versus time graph. Now, we don't want to write this out in full words every time. So we're going to do another shorthand here. And instead of position, because we're talking about things going horizontally, we're going to use the variable x. Because on a number line, if we're moving horizontally, and we're in math class, see we have x and y. So if I'm going left and right, that's along the x-axis. So we call our horizontal position x. Velocity, now this is for a constant velocity. We're going to call that v sub c. Time, we're just going to use lowercase t. Make sure you don't draw a t like that because that looks just like a plus sign. So draw a little curl to it and that'll make it look like a t. And then the last thing, the initial position, we call that x sub 0 or x naught. That 0 tells us, oh, that is the position when the time is 0 at the beginning. Now, each of these things have units. So sometimes you will see the number given to you with some units and it'll help you recognize what quantity it is. So the units of position are meters. The units of velocity are meters per second. The units of time is seconds. And the units of initial position are also meters. So this equation here will predict the future for anything moving at a constant velocity. The general idea is we take our equation, see if we can snag that here. We take our equation and we have 4 variables. 2 of them, or 3 of them we will know, and 1 of them will be what we're trying to figure out. So let's say we're trying to figure out what speed is the object traveling at, what's its velocity. We will need to know its ending position, how long, or let me do this back. We will need to know where it started, we will need to know where it ended, and we will need to know how long it took to go from its starting position to its ending position. We'll plug those values in and it'll give us the velocity. And that works for any combination. Maybe we know how fast it was going, but we don't know how long it took. So we need to know where did it start, where did it end up, how fast was it going, and then it'll tell us the time. Sometimes we won't know how far or where it started and where it ended, we'll just know how far. We can actually rearrange this equation. I'm going to subtract x sub 0, x naught from both sides, and I'm going to get this equation, x minus x naught is equal to the velocity, which is constant, times the time. Now, the ending position minus the starting position, we call that the change in position. If you look at your bank account, if you take your ending balance minus your starting balance, that'll tell you how much your bank account went up or down. A shortcut way for that is delta x. That just means change in position. So that just means, well, I guess x minus x sub 0. So delta means take the final value of whatever it is minus the initial value. So sometimes we'll write this equation as delta x equals velocity constant times time. All this means is how far did it go? So maybe we don't know where it started. Oh, it went 30 meters. but we don't know where it started and where it ended, we can just put in 30 for delta x. So this equation will predict the future it'll describe the motion for anything moving at a constant speed. Now, if we have changing speed, it's a little bit more complicated. Now, you may look at this graph here for changing speed and say, hey, it's the same graph. You just did that one. But it's different. The y-axis matters, and it matters a lot. So this is a velocity graph. We're going to do the same approach as we did last time. We're going to rewrite the equation, y equals mx plus b, but with our variables from this graph. So instead of y, that's going to be velocity. Instead of slope, that's the acceleration. Acceleration is the rate at which velocity changes. It's how quickly the velocity is changing. For the x variable, now this is confusing because in math class they use x variable, we use x for position. The x variable in this graph is time, and the y-intercept is initial velocity. Now, again, we don't want to write out all those words every time. We say the words, but when we write it out, we can write v for velocity, a for acceleration, t for time, and v sub 0 or v naught for initial velocity. The units, meters per second for velocity. For acceleration, acceleration again is how quickly the velocity is changing. So we may have an acceleration, give you an example of 5, maybe 5 meters per second every second. So that means we're either going 5 meters per second faster every second or 5 meters per second slower. So for instance, like on your speedometer on your car, maybe we have something, maybe here's your speedometer. So we start off at 0 and we go 10, 20, 30. Our acceleration would be how quickly that would happen. So this would be a very small acceleration, taking a long time. And this would be a very fast acceleration. Vroom. Still end up at like the sound effects there. Still end up at the same final velocity, but it's how quickly we got there. Okay, so it's for a car, it'd be like, oh, I'm going 10 miles an hour faster every second, or maybe I'm only going 2 miles an hour faster every second. All right, so this will help you predict the future for something with a changing velocity. Note there's nothing about position in here. So we need an equation with position. So here's our position versus time graph. It's curving now. This is a quadratic, so we're going to use a quadratic function, just like you do in math class. The equation, how it works out, is a little more complicated. But for the y variable, it's still position, horizontal position, which we call x. The coefficient here is 1/2 the acceleration times the time squared, which is our horizontal variable. And then we have initial velocity times time plus initial position. So this one is a little bit more complicated. If we write it in just variables, it looks like this. I wrote acceleration there. 1/2 at squared plus the initial velocity times the time plus the initial position. So again, we have an equation. This will allow us to predict the future for anything moving with a changing velocity. So let's say I want to know how long it took. Well, I need to know where it started, where it ended, how fast it was going at the beginning, how quickly it was changing its velocity, and then that would tell me, could solve that for the time. Remember on the last one, on the constant velocity, how we did this, we moved this x naught over to this side. We can do the same thing here as well. So so we have x minus x naught, subtract x naught from both sides. But instead of writing that as x minus x naught, we can shortcut it and we can just say, oh, that is delta x. That's how far. And that'll just tell us how far. It won't tell us necessarily where we started or where we ended, but how far. So you have two of these equations. How do you know which equation to choose? Or we have three equations. How do we know which equation to choose? Well, the first step is this problem a constant velocity problem or is it a changing velocity problem? If it's constant velocity, use this equation and you're done. If it's changing velocity, you gotta choose which one do you use, this one or this one? So you'll notice that this equation, the lower one, has position and it has how far in it. And this equation does not. So if the problem is asking you or has information about how far the object went, you want to use this equation here. If it doesn't give you anything about how far or the starting position or the final position, and it's not asking you to find that, you'll use this equation here. So here are some problem solving steps, 1, 2, 3, 4, 5. You can read through those. Here are 2 example problems. I'm not going to work through those. I think it's going to be pretty self-explanatory, but you can see everything there. The one on the left is a constant velocity, and the one on the right is a changing velocity, speeding up. So that's a quick overview of word problems using our kinematics equations or our equations for motion.